Hello, welcome to Maths with EJD. This is the second video on generating functions, and here our focus is on ordinary generating functions. We start with a formal definition, and notation of ordinary generating functions. We already got introduced to the concept in the previous video. Um, so an ordinary generating function, an ordinary an ordinary generating function OGF for short is a formal power series used to encode a sequence an from n greater than or equal to 0. All right. So the ordinary generating function, okay, I guess I want to color code at this point. The ordinary generating function of a sequence is defined as usually we like a of g of x, but here we can say a of x in summation from n equals 0 to infinity, and that is an x raised to power n. This is the ordinary generating function for a sequence. So here, say where an represents the nth term. This represents the nth term of the sequence and x is a formal variable. Okay, now let's move on to how to deriving ordinary generating functions for simple sequences. How do we do that? Okay, number one, we have the constant sequence. The constant sequence is a sequence of 1 all the way. So we have the constant sequence where an is equal to 1. Okay. So here, the OGF is AX equals summation. You know, the general formula is an x raised to power n, right? So that will be AX equals summation from n equals 0 to infinity for, instead of an, now we have 1 all the way. Then you have x raised to power n. And if you do this, this is basically when x is equal to 0, you have 1. When x is equal to 1, you have x. When x is equal to 2, you have x squared and x cubed. And that goes on until at infinity, that's like 1 over 1 minus x. If you do the sum to infinity, and this only holds for x lying between -1 and 1. Okay, we've seen this a lot. Okay, so in short, we are saying that the sequence 1 1 1 actually maps to the generating function a of x, which is equal to 1 over 1 minus x. That's the essence. That's simply what that means. Okay, so that's the constant sequence where an is always equal to 1. Okay, so let's go to when we have like a linear sequence. You have a linear sequence. For a linear sequence, right? That is an raised to power n, an raised to power n. So for a linear sequence, an raised to power n, of course, you already know the general formula. So we can just say that the OGF, the ordinary generating function, is The ordinary generating function is a of x, which is equal to summation from n equals 0 to infinity. Instead of an now, right, the sequence, you have a line, n multiplied by x raised to power n. And if you do this, this is actually the same thing as, of course, if you do 0, that's 0. Then if you do 1, that is x, right? If you do, so that's x. If you do 2, that is 2x squared. And that goes on like that. So this is, you will discover that this is actually the same thing as x d dx of 1 over 1 minus x. Now, this is familiar, right? This is for constant sequence that we just did up there. So it means that if you differentiate the ordinary generating function for the constant sequence and multiply by x, right? You end up getting this particular one. So in the end, this is actually the same thing as, if you differentiate this, of course, this is x over 1 minus x all squared. Okay. And that also holds for only x less than absolute value of x less than 1. So in short, we are saying that the sequence 0, 1, 2, 3, okay, maps to a of x equals x over 1 minus x all squared. Of course, given that x lies between minus 1 and 1, that's the constant, that's the linear sequence, okay? So we can go on and on like that. Now, let's talk about, generally, now, if you want to derive an ordinary generating function, all you just need is the nature of the n. Is it constant? Is it linear or whatever? Okay. Now, let's look at some operations with OGFs. Operations operations with OGFs, ordinary generating functions. First of all, we look at the addition operation. Addition. So we can do addition with ordinary generating functions. So we say here that if a of x and b of x are ordinary generating functions for sequences, an and bn, then we can say that the sum of the generating function c of x is just ax plus bx. And so this sum actually corresponds, that corresponds, it corresponds to, so that corresponds to the sequence an plus bn. So that means that if you have these sequences, just add them up correspondingly and you are good to go. And that takes care of addition. All right. So we can also talk about multiplication of OGFs, right? Multiplication. So the first was addition, now multiplication. All right. The OGF, the ordinary generating function for the convolution of two sequences. That convolution is called the Cauchy product. Cauchy product. So the OGF for the convolution or Cauchy product of two sequences is given by C of x equals the product of the two generating functions, C of x times B of x. So such that Cn, a constant, is actually summation from k equals 0 to n of ak b n minus k, like this. All right. Example. So example, multiplying, multiplying, multiplying a of x, which is the same thing as 1 over 1 minus x, and b of x, which is equal to x, actually the OGF, yields the OGF c of x equals x over 1 minus x. Just that simple. And this corresponds, so corresponding, corresponding, corresponding to 0, 1, 1, 1, and so on and so forth. Okay. Okay, then we also have another one called shifting. We have another operation on OGF called shifting. Shifting. So addition, multiplication, and shifting. So multiplying a generating function a of x by x raised to power k shifts the sequence. So it will shift the sequence, shifts the sequence to the right, by k terms. So for instance, you have a of x shifting to x raised to power k times a of x, implying that you now have a naught, a1, a naught, a1, and all that becoming, okay, let me move that down to make it clearer. So a of x moving to x raised to power k, a of x actually implies that you have a naught, a1, and all that becoming 0 k times. Okay, 0 k times. So you have 0, 0, like 0, 1, 2, 3, up to k times in short. Then before you now have a naught, a1, and so on and so forth. So this is now with k leading zeros. So if you multiply by x raised to power 2, you have two zeros. X raised to power 5, you have five zeros before the normal sequence. So with k leading zeros, like that. Okay. So let's talk about simple combinatorial interpretations. Simple combinatorial application interpretation. Simple combinatorial. Combinatorics is all about is about counting, right? Simple combinatorial interpretations. Okay, so first we talk about counting with replacement. Counting with replacement. Now, when I did I think probability, when I did probability, when we talked about random sampling, this idea of counting with or without replacement came up. Okay. So the ordinary generating function 1 over 1 minus x, that's for the for constant sequence. The OGF, this actually represents the sequence, to represent the sequence of all non-negative integers, that is 1, 1, 1, and so on. Useful for problems, involving unrestricted choices. Okay. Then the second interpretation is about weighted counting. Counting with weighted counting. Okay, so the ordinary generating function for linear sequences now, this is where you now have x over 1 minus x all squared. This actually corresponds, to counting, where weights increase linearly. So you can see the x at the top as a weight, where weights increase linearly, such as distributing, n identical items, into beams. Okay. All right. Now, in conclusion, right? Conclusion, by mastering these basics, right? Um, we can derive OGFs for fundamental sequences or fundamental sequences and performing basic operations and performing we can derive OGF OGFs for fundamental sequences and perform uh basic operations in combinatorics and discrete mathematics. In combinatorics and discrete mathematics. Okay, based on all the things we've learned. All right, so that's the end of this video. If you have not subscribed to this channel, please do that right away and hit the notification bell so you can always get alerted each time a new video is released. For those who have subscribed, thank you so much for that. Then, of course, comment, let me know how helpful these videos are, and let me know if there are problems you'd like me to solve or topics you'd like me to teach. Then like and share so that more people can have access to this great content. Till I come your way again, keep enjoying maths. Well, bye.